A very good afternoon, everyone, and welcome to the 6th BEX Asia Masterclass of 2025, organized by RX Singapore. BEX Asia is, of course, the largest and longest running trade exhibition for the built environment industry in Singapore. We attracted 10,000 attendees in our 2024 edition, and our 18th edition this year is expected to be even larger and better. BEX Asia is the anchor event of the International Built Environment Week, or IBEW, which is jointly organized by the Building and Construction Authority of Singapore and RX Singapore. This year's conference program expert series will bring various case studies, best practices, and deep dives in the areas of digital construction, construction efficiency, sustainability in construction and data centers, and of course, green mark and retrofitting. We will also be hosting the IBEW Industry and Awards Dinner on the 3rd of September, where BCA will be presenting its top industry awards, the Project of the Year, and Company of the Year awards. BEX Asia and IBEW will take place from the 3rd to 6th September 2025 at the Sands Expo and Convention Centre, so do mark your dates and make sure you join us then. Now, I trust that everyone has had a great week thus far, and today's masterclass is in collaboration with ebm-papst on a topic that always attracts a lot of interest: HVAC and low-carbon buildings. We had an overwhelming number of registrations from Singapore, Malaysia, Indonesia, Philippines, and other ASEAN countries, but we also have people from further away like India, the United States, and even Peru joining us today. So to all of you, a very warm welcome and thank you for joining us today. Now, today's topic is building integrated HVAC design for low carbon buildings. Now, in the journey towards low carbon and net zero buildings, HVAC systems play a critical role in reducing operational emissions and enhancing energy efficiency. Now, this masterclass highlights the importance of integrating HVAC designs within the broader context of sustainable architecture, emphasizing early stage coordination between systems and structure. We'll also be exploring advanced strategies for energy efficient cooling and ventilation, with a special focus on next generation EC, or electronically commutated technology. And we will learn how EC motors can contribute to lower energy use, quieter operation, and better controllability, all while supporting our long-term sustainability goals. And I'm really happy to have with me today Ricky Chua, who will be presenting this masterclass. And Ricky is a senior sales manager at ebm-papst Southeast Asia Private Limited with over 2 decades of experience in the engineering field. At ebm-papst, he has managed various portfolios, including telecom and air conditioning and commercial ventilation (ACV) segments, where he specialized in fan solutions. He played a key role in the introduction of EC fan grid solutions to Southeast Asia, which has significantly impacted the ACV industry for the better. Ricky has also facilitated remarkable results and efficiency improvements in applications such as fan coil units and air handling units. Now, in the recent years, Ricky has also expanded his expertise to include Internet of Things, by combining his knowledge of high-efficiency ventilation solutions with IoT technologies. He is well positioned to help you further customize the energy consumption of ACMV systems, and he holds a Bachelor of Science Honours in Sales and Marketing from the Management Institute of Singapore, awarded by the University of Bradford. So, Ricky, can I now invite you to turn on your camera and say hello to everyone?
Hi, everybody.
All right, Ricky, good to have you with us again today.
Thank you very much for having me.
I trust you have had a good lunch earlier and you're all ready to go with our sharing session today.
Yes, I cannot wait.
Okay, great. Now, ladies and gentlemen, before we begin, please note that the masterclass is scheduled for an hour and you can always ask questions using the Q&A function at the bottom of your screen. So without further ado, Ricky, can I hand it over to you to take us through the great information on how to design HVACs for low carbon buildings? Over to you,
Sure.
Ricky.
Thank you. Okay, I think first of all, let me share my screen. Okay, a very good afternoon, everyone. My name is Ricky Chua. It is my pleasure to be here with all of you today. and appreciate your taking the time to join this session. So over the next 1 hour, I'll be diving into building integrated HVAC design for low carbon building, exploring key insights and practical application that could be relevant to your work. Sorry about that. Okay, so I think first of all, I would like to talk about ebm-papst. So at ebm-papst, engineering a better life is our philosophy. It illustrates the importance we place on our goal of helping to make the future better. And with our increasing efficient and intelligent solution, we are helping to make the world a more sustainable place. So looking at our revenue for fiscal year 23 and 24, we had a good year. Our turnover is 2.3 million euros. And from these slides, you can see that our R&D investment is at 5 to 6%, about 137 million euros per year. So we spend a lot of money, into investing in our technology and innovation in the objective of improving our product. So our philosophy is that every product or new product that we introduce, it must be better than the predecessor. So we look at the numbers in Southeast Asia, and Singapore being the headquarters. Indonesia, Malaysia, Thailand, Philippines, and Vietnam actually reports back to Singapore. And we are proud and very excited to share with you that by end of this year, we would have a assembly plant in Malaysia. And this allows us to support and provide instant response to the customer in terms of stock availability, thereby reducing the waiting time, reducing lead time, and providing a better service to Southeast Asia. So at ebm-papst in Singapore, actually we cover a very wide range of products. But globally, we actually cover not only heating, air condition, and commercial ventilation. But in Singapore context or Asia context, of course, we are not using a lot of heating. But especially in HVAC, we cover refrigeration, transportation, clean room, residential, renewable, industrial, and ICT, all across industry. And just to give you an idea of the products that we have, so when you reach home, for example, actually there could be an EC fan in your house because we have products that are being used in microwave, fridge, and even wine chiller. And the moment you step out of the house, be it you take public transport, or even if you drive a car, we have fans that are used for seat ventilation, fans and blower that are used for SBS buses. And maybe shopping around in a supermarket or convenience stores. We have fans that are being used for the condenser, the vending machine, and the showcases. Not to mention that actually we are also very strong in the segment of ACMV for commercial and industrial building as well. So ebm-papst was founded in 1963. And in 1965, actually the first external rotor was born. Okay, that's when we developed the first external rotor motor. And with the external rotor motor, we actually invented the EC control in 1965. So we are quite a few years from now developing and improvement the technology of the EC fan. So in these days, if you want to control an AC motor, okay, you will need VFD. But for us, during that year, we control a fan with electronic commutation since then. And if you can see from this chart here, during those times, you will need 7.5 kilowatt power just to move 10,800 cmh of air at 1000 Pascal, but today you would only need 4 kilowatt. So the reduction and improvement in the efficiency of a fan is tremendous, almost about 40–50%. That is because we put a lot of emphasis in the R&D, adding manpower, putting resources to develop new products. So today, with our EC Gen 3 motor, we are actually at IE5. The efficiency of the motor is above 90. So when we look at a low carbon building, what is the definition of a low carbon building? So low carbon building focus on reducing carbon emission across the building whole life. So from the material use, like low carbon concrete or recycled steel to the construction process, the building energy used during operation, it can be include energy used, but also considered embodied carbon, the emission from producing and transporting building materials. So basically, there are two types of carbon emission, the operational and the embodied. So for the operational, so this comes from the energy used to run the building over its lifetime, be it for heating or cooling. Lighting and appliances, water heating, plug load, these are long-term ongoing emissions that are being released during building, the lifetime of the building. So for embodied carbon emission, these are emissions that comes from the material and construction of a building, which includes extraction of raw material, mining, logging, manufacturing, example, cement, steel, glass, transport of material to site, construction processes, maintenance, renovation, and end-of-life demolition. So when we talk about zero carbon building policies, there are basically 5 pillars. But for today's session, we will focus on the first pillar, the energy efficiency. So active strategy to improve energy efficiency by integrating advanced HVAC system and technology into building. And our objective is to reduce scope 1 emission in HVAC. So one of the way is to switch to EC fan. So when we started in 2015, introducing EC fan, using multiple fan to replace a single AC fan, we see a lot of saving, very significant. Savings that range up to 60–70%. And until today, actually, we are also seeing very high energy savings result, not only in Singapore, but the rest of the Southeast Asia country as well. In recent years, we also introduced IoT to our EC system, which enable real-time monitoring, predictive maintenance, and adaptive operation based on environmental condition, which at the end of the day result in reducing the carbon emission for a building. So why HVAC efficiency is key to meeting net zero goals? So any energy consumption in a typical building, be it commercial, industrial, or hospitality. BCA actually published that energy usage, especially for ACMV, constitute close to 70% in the whole building. So it's a very significant amount. So if you are able to reduce, say for example, 30% of this energy consumption, you would be able to save about 20% of the saving for the whole building. And that's a lot. And for cooling and ventilation, we have seen result that is as high as 60%. And that will even, add on to your saving for a building. So therefore, reducing overall ACMV energy consumption will be effective in reducing overall energy consumption of the building. in any country. So the design principle of AHU system. So I think first of all, before we look at the system, we would like to share with you which fan or what type of fan is more suitable in a ACMV environment. So at ebm-papst, we produce both axial fan and centrifugal fan. So we know that in the AHU market, all this while we are using centrifugal fan since day one. But in recent years, we also see a market using axial fan. Now, what is the difference and which one is more suitable? So let us look at axial fan first. So axial fan, being axial fan, the air flows through it parallel to the shaft in axial direction. The typical application is ventilation or exhaust. If you want to move air from point A to point B, usually axial fan is deployed because it has a higher velocity and it will reach a further distance. Okay, so comparing to a centrifugal in terms of the same diameter, axial fan will give you higher airflow, yeah, at a higher, longer distance. But the disadvantage is it will also produce a higher noise level, okay, generating lower pressure as compared to axial fan. So axial fan, the airflow is radially, okay, because some fans actually are designed to flow perpendicularly. But at ebm-papst, due to the design of the diffuser, the air is pushed out radially from the circumference. So application is ACMV, anything that is ducted or a positive plenum or negative plenum, you will need a centrifugal fan. It produces higher pressure from the same diameter as an axial fan. It generates a lower noise running at a lower RPM, generating the same pressure. So the second characteristic or important parameters that we want to look at is pressure. So pressure, what is pressure? So there are actually three definitions: total pressure, dynamic pressure, and static pressure. So to understand the difference, basically we have to use a pitot tube. So having fluid, flowing through, how you get static pressure is the measurement will be accurate when there is least turbulence. That is static pressure. And the only way to get total pressure is when the fluid push through, and then it will give you the velocity pressure, static pressure that makes up total pressure. So in order to obtain the dynamic pressure, you would have to subtract static pressure from total. So from here, static pressure overcomes the resistance within the duct, whereas dynamic pressure is the velocity pressure, the movement of the fluid or the media, it could be air, within this tube. So in a ACMV environment, do you need static pressure? Yes. So static pressure is very, very important. So why? Let us look at it. So in a CFD simulation, you can see that a centrifugal fan will give you a wider surface area moving at a slower speed. When you have a slower velocity, you have a higher static pressure. Therefore, higher static pressure overcome the resistance within the duct. As compared to an axial fan, the axial fan actually spin at a faster speed, pushing higher velocity, and you can see that the velocity is focused in this red ring. So you notice that the center has a lower velocity because at the center of this axial fan is the motor that obstructs the flow. Why is static pressure important? So when you design ACMV, okay, static actually overcome the resistance within the ductwork. Static pressure also ensures that air is evenly distributed throughout the building. And then the third thing is that static pressure overcomes the static resistance from the filter, the coil, and the damper. So what is dynamic pressure? I think for dynamic pressure, the way I look at it to explain it a bit more clearly is that, let's say, imagine you were squeezing the end of a water hose. So the water jet sprays out from the hose. So instead of water, if this is air, so this will be a high velocity air moving through the duct. If there's any turn or bends within the ductwork, a lot of turbulence will be created. And this turbulence will actually reduce the efficiency and the flow of the air throughout the duct. And dynamic pressure actually, will reduce the efficiency, and then it will cause more harm than good within the ducting system. So in terms of fan, in terms of pressure, in terms of type of fan that you use actually affects the efficiency of the system. So why EC technology? So we'll explain to you why EC centrifugal fan are being used. So first of all, what is EC fan? So EC fan consists of a control unit, a motor, and an impeller. So in the control unit, you can actually read the parameters within the control unit with high level, RS485. You can read out the speed, you can control the speed, be it analog or digitally. You can actually set the PID control. You can also have it as a closed loop or open loop system. So on the motor portion, we have an external rotor design with a permanent magnet that is installed within the diameter of the rotor. So without an electromagnet installed, a permanent magnet does not require electricity, therefore reducing energy consumption. And because of its compact small size, heat dissipation is also a lot better. And this reduction in heat actually turns into real power to rotate the rotor. And at the end of the EC fan, we have a composite impeller, a light composite impeller. And this impeller has very intricate design that actually converts the dynamic pressure to static pressure, which is required to move air through the duct. So ebm-papst is one of the leading fan manufacturer globally across all industry. They design the electronics in-house, the motor, and the aerodynamics. So our core competency are in motor technology, aerodynamics, and electronics. We master the perfect interplay of the three disciplines like no other. We are the first in the world. We combine benchmark motor technology with intelligent electronics and aerodynamically optimized design. We set global industry standard based on that all-embracing approach. So this motor is harmonized with the electronics with the aerodynamics, and they work perfectly together to produce a wide and highest peak efficiency point for all users. So now let's take a deeper dive into the electronics. So the brain of it is the EC, electronically computation of the rotor. So it sends a signal to the rotor to get it to turn. Because this design of the electronic actually has feedback from the Hall sensor. It knows exactly the rotation, the number of rotation of the rotor. So it is very, very precise. So it allows precision in speed control. And within the electronics, there are a lot of components that are added to enable it to have this soft start capability. That means you can start 10,000 fan, 20,000 fan all at one go. It has the motor protection, sine filter, EMC filter, all built into the electronics. And within the electronics, you are able to control it via RS48485. You can also control it via low level, which is 0 to 10 volt or 4 to 20 milliamp. So the benefit of having RS485 doesn't stop here. It enables the fan to talk to each other. It enables the fan to also talk to other devices with RS485 protocol. So it is more efficient and it enables the control of the entire system. So there are a few different types of control. The oldest and the one that we started with is master and slave. This is usually deployed in rooftop condenser fan, where one fan runs at a certain speed, the rest of the fan will follow. You can have it run with a DDC. You can have the fan to be connected to BMS as well. So depending on the type of application, you can control it differently. So on the permanent magnet, it gives you a higher efficiency, variable speed control. It is very, very compact in size. A single fan for 500 diameter impeller, it can reach a pressure point about 1,200 and produce about 10 to 12,000 cmh, and it weighs only 50 kilo. So it's very light and very efficient. So it is brushless. That means there's no dust generated. It has also a very high torque. And due to an in-house design, an EC fan at a certain point, we can change the power range or the peak torque of the fan. It is direct drive, all integrated together. It provides a plug-and-play solution. You can just pump in a signal and you can run the fan. External rotor design, which give you a very compact dimension, very low vibration because it is balanced two plane in the factory. And we can reach a higher torque even at low speed. So some of the distinct feature of our fan. I think one of the proud design would be the aerodynamics. So with our Gen 3 composite impeller, we can achieve about 72% in static efficiency. That's very, very high. As of now, we do not know if there's any supplier that can attain and achieve this high efficiency. We are coming up with our next generation impeller. For the same diameter, it can reach even higher operating point. So every component are optimized for each other to reduce losses and also to increase efficiency. So every fan, EC fan that is being shipped out from factory, it is two planes balanced. So in our lab, we try to run the fan without securing, which you can't do that. So we did that. And the fan at 50% does not vibrate. So that is how stable the fan is. So another feature that we are very proud of is the active harmonics filter within the fan itself. So it can keep the pitch level below 5%, even with multiple fan, right down to 10% hard load. We'll share more about the harmonics of the active PFC fan later part of the slides. So the feature and its benefit, first of all, you have state-of-the-art impeller. They are optimized, less noise, improved airflow. Motor, with the IE5 standard minimum 90% efficiency, high power density with very low structural motor noise, very balanced as well. Electronics, it converts AC to DC because it's a DC motor. It provides a very wide voltage range. For example, three-phase 380 to 480. Any fluctuation in voltage will not affect the performance. Increase reliability, enable fan to talk to BMS. You can actually hook up to other sensors like differential pressure sensor. Then it becomes a standalone unit. No VSD is required, and a lot of protection are built into the fan. It's a full solution design with the highest possible fan static efficiency. So now we'll share with you the adoption of EC technology, the case study that we have done. So this is a aerospace manufacturing facility. So within deployment, the end user actually saves up to 70% of the energy consumed in the building by replacing 7 AC belt fan, centrifugal fan with our 14 of our EC centrifugal fan in the manufacturing facility. So they reduce the consumption from 31.8 kilowatt per hour to 16 kilowatt per hour per month. So equivalent saving of about 48%, reducing carbon footprint to 6.3 kilowatt per month. So if we just look at the time lapse of a manufacturing facility that we have actually done to share with you how it's being done and the energy saving that we are able to achieve. So you can see that it has a saving of an impressive 82%. So EC centrifugal fan grid is installed. So it has a very wide voltage control range, 10% to 100%. That means if your fan runs at 1000 RPM, you can run it as low as 100. And because we design the components in-house, we are able to widen the optimal efficiency range of the operating point. So we also minimize the flow loss from the impeller design, reduce the noise, and we know and can adjust the flow volume and the operating point with energy consumption value with our very precise Fan Scout software. So very flexible in possibility with a lot of options that we can also share later. So the above enable high energy efficiency, operational redundancy, improve end user comfort, plug and play compact, lower operational costs. So in another data center case study in Singapore, we managed to reduce about 37% of energy consumed in data center. So this is a cooling tower project. We replaced 54 with 400 of EC fan. We're able to reduce from 580 kilowatt per hour to 330 kilowatt per hour. The saving is 46%, very significant, and reducing 111 kilo of CO2 per month. So this value are tabulated and calculated by the end user. Another time lapse for cooling tower that I will share with you. Okay, for the cooling tower, we are using our EC axial fan. And for one cell, we are replacing 4 EC fan. So basically, it gives you a more uniform flow. It draws air, the hot air out from the cooling tower more efficiently because it has a wider surface area. So same thing, because EC fan, we are using the same motor, but with a different impeller. It has a wide speed control, high power density, top protection against splash water. So basically for cooling tower, we have a different protection. So it undergoes a lot of rigorous tests. One of them will be the salt fog test, 2000 hours, high stress test, which is not actually indicated here, but we can share with you what are the tests that it has gone through. Thermal shock test as well. for the fan, and all the components are optimized again for each other. And these are the same thing as the centrifugal fan, so I will skip this. So basically, the fan can be deployed in the air handling unit, cooling tower, exhaust supply fan system, condenser, which this is one of our core business in the earlier days. It is now, as we speak as well, evaporator fan for those cold room, fan coil units, fan filter units, crack units. So I'm looking at advancing HVAC efficiency with the next generation EC technology. So in the journey for digitalization, we've incorporated vibration sensor, hall sensor, temperature sensor to enable data-driven decision making. So a normal intelligent fan becomes right now a smart fan. So basically what we can do with it is that we can monitor the health, we can predict, maintenance time, optimize of the fan performance, extension of fan lifespan, servicing and exchange on demand, 100% safe operation, and avoidance of harmful operation condition. So what is avoidance of harmful operation condition? Let us look at it. So with the vibration sensor, okay, so in its delivered condition, if you run the fan on its own, it could have a certain resonance response, for example, as an example. But when you install the fan in a, say, for example, ASU, the resonance response may change due to the installed environment. And if, for example, the fan actually exceed the preset value, the limit value can be implemented or input by the user. If it exceed the value, you can enable the software to mask up this area. That means the fan will not run at this RPM. So it will actually prolong the life of the fan, and it will prevent premature failure of the fan. So our next generation three-phase or Gen 3 active PFC has a 4 kilowatt motor. The next generation will have about 7-8 kilowatt power. The same reinforced electronic surge protection 6 kilowatt with motor for universal and worldwide use. The same fan with the measured performance here, you ship to Philippines with 60 hertz supply, it will perform at the same performance. It will not change. So the electronics is replaceable. If the electronics is damaged, it can be replaced. So every fan has a onboard vibration sensor, a new Modbus version, programmable interface. And this unit here, for now, it is being localized in China. So the new model that will be available end this year, the 7 to 8 kilowatt version, will also be localized and produced in China. So for data center, this is a very critical and important topic because data center requires PHDI, harmonics, to be below 0.5. And also in terms of power factor, above 0.9. So this is so-called the target for a EC fan or any other fan for that matter. But present moment, some of the data centers still have external PFC installed. So with the active PFC EC fan, you do not need to actually install or purchase external active PFC. Every fan comes with it. And let's take a look at what are the advantages. So in a study that we did with our counterpart in Germany on a small data center, 3 megawatt. So we change out conventional fan to an active PFC fan. So with a reduced harmonic and an improved power factor, you can reduce the need to oversize the transformer and generator because it minimizes reactive power and harmonic distortion in the electrical system. It also ensures that the fan draws current in phase and voltage, achieving power factor close to 1. So it prevents this harmonic from occurring, leading to a cleaner power supply and reducing strain on the electrical infrastructure. So active PFC also allows for smaller, more cost-effective power supply component. So all the cables can be reduced as well. So you can have a smaller footprint, save space and construction costs. So all in all, in that study, 38% cost savings are possible. So we also take one step further. We compare our active PFC fan with a competitor. So basically over here, we have a perfect main incoming with no harmonic distortion. These are tested in the lab. So with ebm-papst, our THDI is less than 5% when the load actually reduced to 10%. But for competitor, when you reduce to 5%, it can only be reduced to 18% speed. Okay, anything below, it exceeds 5% THDI. So similarly for power factor, at a perfect main, ebm-papst, you can reduce the speed down to 10%, still maintaining the THDI of within the range. Competitor, when you reduce to 31%, the PF power factor actually also reduces. So we tested in an environment whereby there is a lot of harmonics in the main. So ebm-papst, we can still maintain our THDI below 5%, whereas for the competitor, it's all over the place. They are not able to maintain the THDI below 5% at all. So in terms of power factor, similarly, we are able to maintain our high power factor value, but the competitor cannot maintain it beyond 0.8. So therefore, for active PFC, we address the following challenges. So the last topic that I will dive into will be on the IoT, because as part of our commitment to innovate and also to improve efficiency, we are integrating EC fan with IoT technology. So this transition allows us to enhance real-time monitoring, predictive maintenance, and intelligent control. So this unit here, we call it the Intelligate Mesh, is developed locally based on our needs and requirement. So the main purpose is to connect and interconnect all our fans together. It can act as a mesh. It can communicate with one another, 20 to 50 meter, in the line of sight, no blockage. It can also act as a mesh. So you can actually read multiple fan all at one time instantaneously with very fast response. High-level Modbus sensor and device can be seamlessly integrated via quick interconnection. So what is in this controller? So it has temperature, humidity, and carbon dioxide sensor. MQTT sends it direct to cloud, Wi-Fi interface, and Wi-Fi. So we've tested with LoRa. So LoRa could not handle the bandwidth because there are so much data actually coming to and fro from the fan. LoRa, we tested LoRa for one unit of fan, and it is quite slow, not to mention multiple. So basically, Wi-Fi is the more suitable protocol, and we adopt Wi-Fi for our Intelligate Mesh controller. So it has all this connection that you can utilize. And importantly, it also has Modbus as well to be connected to our fan. Low level, high level communication, tacho readout for compact fan. So let's say if there are fans that are being used in data center with low level tacho output, we can read it as well. 0 to 20 milliamp input. So a case study. So this is a case study for a transport facility in Singapore, demand control toilet ventilation. So this transport facility operates 24 hours. So the pain point is that because you run 24 hours, the ventilation fan run 24 hours as well. So energy consumption is very high and there isn't any control or demand control for the fan. So the solution is to retrofit the AC fan to an EC ready-cube fan solution. This is the ready-cube. Second stage will be to implement the solution. So we have an intelligent mesh connected to the fan as well as some sensors. This is people counting sensor and some other sensors that are connected, linked to the toilet. So we monitor the number of people going in, and this is the requirement from the end user. At 20 air change, so they calculated the air change, the fan will run at 30%, 40%, when they are 5 to 10, you'll be able to achieve 35 air change per hour. And when there's more than 10 people, you will run at 50%, with 30 air change. So this is higher than normal, and this is their requirement. So at night load, the fan will run at 10%. So it's 24 hours demand control. We are able to save more than 60% and also eliminate their pain points. So the system works this way. One set of toilet consists of male, female, handicap. We have a people counting for the male, female. None for the handicap. Usually there's one, cannot be more than that. So we did not actually add those in. So every toilet will have one, okay, integrated link to the sensors, and then the data will push back to cloud. So the algorithm is all in the cloud as well as the controller. So you can store the logic here as well. And if there's a break in communication, the mesh controller, the fan will still operate. Okay, that is the end of my presentation. Thank you for attention.
All right, thank you very much, Ricky. Quite a fair bit of things you've covered over there. The
Yeah,
one that really stood out for me was how you helped a customer save 266,976 kilowatt hours per month. Now, I did a quick sum. If you were to take the cost of electricity in Singapore for a household, if that's a household at 35 cents per kilowatt hour, you're saving close to, my maths here said that you'll be saving close to $93,000 a month from
yes,
your
and
electricity
that's
bills.
impressive. And actually, if you talk to some other users, actually some of them are saving a lot more.
Mm,
Yeah,
definitely. So it's not just it's really a very ROI that you can actually see for yourself, right?
yeah. So I think
So
beside
mhm,
ROI, the other thing that actually we are able to achieve is thermal comfort. We
mm,
balance between energy saving and also deliver the sort of level of comfort that is required.
yeah.
Yeah.
Excellent. Now, Ricky, we have a couple of questions from the audience here. So I'll take some from those who submitted questions during registrations, as well as those who came online. Now, we may not have time for all, but don't worry. The questions that has been asked, if we didn't cover them, we will be sending your contact details to ebm-papst, and they'll be able to follow up with you, especially if they are very technical questions. You started with about talking about the static pressure. So one of the question here is, what is the possibility for EC fan to cope with high static pressure specifications such as 2000 to say 3000 pascals?
Oh, wow, that's a good question. But I think this question come up quite frequently. So
Mm-hmm.
basically, in our standard series, we can cover up to 1008 to 2000 Pascal, for commercial industrial grade, and that's more than enough.
Mm-hmm.
So for a high pressure requirement, we may not be able to reach 3000 at this moment, but
Mm-hmm.
we can easily cover up to 2005. Then
Right.
again, beside pressure, the other factor or parameters that we need would be the airflow. At 2005 or 3000 Pascal, what sort of airflow are we talking about? So, of course, 3000 we are not able to reach, but at 2005, which is our max, what sort of airflow are we looking at? Yeah, so that one, because if you use multiple fan, if a fan can produce, say, for example, 2000 Pascal at 10,000 cmh. So if you need 100,000, then you would need 10 fan. So because you are connecting them in parallel, so the airflow actually stacked up.
Mm,
Yeah.
all
So
right.
we can reach out to this user, if he has some of these requirements and see how we can mitigate and meet that requirement.
You might have very specific, perhaps to be high-end manufacturing or clean room for that.
Yeah, sure. Understand.
Okay. So, next question, a bit technical too. Is there EBM products that are suitable for zone explosion proof? For example, class 2, gas group 2B, temperature class T3.
Yeah, so recent years we've seen a lot of inquiry on explosion-proof products. So yes, we do have, and our fan are actually suitable for zone 1 and zone 2, but not for zone 3.
Mm.
Yes, we do have products for those.
Right.
Yeah.
Okay. And the next one is a question on retrofit. This is very interesting because I think many people here in Singapore may also be aware that the mandatory energy improvement program will kick in third quarter of 2025. So if your building is not very energy efficient, you really need to start looking into this. But can these principles of HVAC innovation be adapted to retrofit, particularly for F&B and industrial exhaust motor systems? And what unique challenges needs to be overcome in high grease or particulate heavy environments?
Oh, okay. That's a very good question as well. I think not only we face these questions from the customer end user, we also have been asked by some of the um, certification board as well. So yes, we do. So I think the challenging part of having fan in a very oily, environment is that this, when it dries up, it will hold up, and also damage the electronics and the motor. So what we did was that we actually built a box. It's like a box fan, but we isolate the electronics from the airstream. So
Mm,
by doing that, actually the electronics are not exposed to the heat as well as the elements from the airstream. And also we are exploring, actually we have some ideas to integrate IoT into the system as well.
mm,
We have been working with one of a OEM integrator. I should say he's a system integrator. So he's looking at automating this process, because for kitchen exhaust, it is very difficult to manually control the exhaust fan. So what we want to do is make it run on demand. So every exhaust hood will have a so-called damper, so a motorized damper, be it 0 to 10 volt or Modbus. So I think 0 to 10 volt will be a lot cost effective. And the other thing that we need to add will be a temperature sensor before the filter of the hood, to sense or detect if there's any heat generated during cooking. So when there's heat, then the fan will start operating. So when there's low load, probably the EC fan can run at a lower load, maybe at 10%. But when heat is detected, the temper will open up, and then we'll draw air from that particular kitchen hood that is actually operating, or when it's cooking. Yeah. So this is a project that we started last year, and we are in the process of fine-tuning and improving the system.
right. So it's really something that you're looking at and will, of
Yeah,
course, keep an eye out for when you roll it out to the market. Yeah.
yeah. But for
Uh,
the exhaust fan, actually, it is right now in the market. We have installed it in Kopitiam, Swensen, some of the restaurant. It is
right.
already been implemented.
Okay.
Yeah.
A question from a live audience here is what is the sweet spot for EC fan within what operating range?
Oh, okay. So that's another very good question. So basically, the calculation of the power consumption or the sizing is very, very different from an AC fan system where you do manual calculation. So right now because every EC fan is measured, it's not calculated, it's measured. So the data that we have are measured data, and this measured data is compiled into a software. And with our software, okay, based on your operating point, when we input the requirement, they will size the selection with the best and highest efficiency for us. So it's quite a simple process. I can show, whoever that needs to know. Yeah, so we size it from a software. So that means they will give us a selection, say, for example, most efficient, say, you say the energy consumption is, say, for example, 10 kilowatt. Second most efficient maybe is 11 kilowatt. So 10 kilowatt, this selection could be maybe 4 pieces of 500 diameter. So the 11 kilowatt selection could be maybe 3 pieces of 560, a bigger diameter fan. So the combination are based on actual measured value from the software. Yeah.
So it's not necessarily a one size fits all, but you can mix and
Yes,
match
we can
your
mix and match.
choices.
Like for example, some property, very big property, they utilize only two sizes. So they fix, okay, I want 500 and 450 diameter, and they roll it up for their whole property. So the only inventory they have is two sizes and two part number, which we stock in Singapore in our warehouse. So they don't even have to actually keep any inventory of any component.
Right.
Yeah.
Okay. And I guess that's also leads to the point that one of the attendees here, if there's one of the EC fan is down, how do you prevent air short circuit? But because most of the times you might be replacing conventionally, you were using one fan, but now you're using maybe two to four.
Right.
So one is down, you still have three working.
Yeah. Okay. That's a very good and common questions as well. Okay, for short circuiting, so it very much depends on the pressure of your system. Say, for example, if your system is, say, about 600 Pascal, in our lab measurement, 600 Pascal, we're talking about 5-6% losses. If your pressure is higher, the losses is higher. So this short circuiting probably I would say is temporarily, because changing an EC fan probably takes up, for those first time installer, maybe 2 hours. For those, very frequent or user that are familiar with a
Experienced.
system, experienced one, maybe they take less than an hour. So it's very,
Mm,
very fast. So you can choose, any weekday, you can just, change it out, no
change
issue.
it.
So, but if your installation is critical, you need,
Mhm.
to really omit this short circuiting, you can just install a damper. But I would really, advise and recommend not to, because it's also increase your static pressure.
Right. Okay.
Yeah.
One quick question here. Any ebm-papst EC fan solution that is suitable for car park ventilation? Yes or no?
Oh, yeah, this is quite a difficult question, because at this point, Class H needs a 250 degrees C for 2 hours, which at this point electronics are not able to withstand. So
Mm,
we don't have that solution for the time being.
But with
Yeah,
all your R&D that you guys invest in, maybe will coming out soon, yeah?
yeah, sure. Yes, we hope to.
All right. One final question because we are slightly over time now.
Okay.
Referring to one of the examples shown in the slide, 7 AC fans were replaced with 14 EC fans. With the higher number of fans, do you require a larger space? Is the footprint larger?
Okay, so for most of the case, if you look at retrofit, if the airflow is high, the impeller for an AC system, usually they use a scroll housing is even bigger. So we have not come across a case whereby EC fan retrofit are not able to be installed in that size. So most of the time we have a lot of spare space after retrofitting. Yeah.
Mm. All right. Okay, thank you very much, Vicky, for answering all the questions and sharing your in-depth knowledge on the power of EC fans and how it can contribute to low carbon buildings, particularly in operational carbon. And we have now come to the end of the masterclass, and the slides from today will be circulated via email to all attendees. For those of you who may had issues with some of the videos, don't worry, we'll be uploading it to the BEX Asia YouTube channel, so look out for that too. And before we clock out, please, we will have a QR code on screen for you to scan to provide your feedback to the masterclass today. And do not forget, mark your calendars down for the 3rd to 5th September 2025 so that all of you can join us at the International Built Environment Week Expert Series, where we will share even more in-depth case studies, best practices, and deep dives into the topics, as well as BEX Asia, where you can source, network, and meet with the best suppliers and industry. If you haven't done so, follow our LinkedIn BEX Asia page and IBEW's LinkedIn page to stay updated on future masterclasses, the expert series programming, and the BEX Asia exhibitor directory. Till then, take care, everyone, and have a great rest of the week ahead.
Thank
Thank
you,
you, Ricky.
everybody.
Thank you,
Thank you,
everyone.
Sabi.